Sorry? Was I pick and pay yesterday? In.
Wait, that's right.
In. I've got this facing the wrong way. Did you see me in pick and pay? All right. Not that I'm a keen shopper of pick and pay. Okay, so Nelly says that he likes his music and he knows the words for it. Anyone else like to tell us what their passions are and what they feel strongly they don't mind doing and they do it well? Anybody else? Sure.
I'm gonna take. You don't have to lock the door. No, you just have to put on the lock. You can just pull it closed.
With the other outside
Yeah.
lock.
I'm going to. Because I bought another lock because I wanted to make copies of this, but then this is the old ones. You see, it's old ones, so they don't.
But I make copies of.
When you want to make a copy, you want to make a copy yourself. Oh, no, not it's
doesn't
fine,
really
but
matter.
then you can just ask again. No, because I think that sometimes other teachers also, I don't know who uses the lab. Like the other day, you know what I mean? Some
I would have to make a copy of that key as well.
just no, yes, okay. But this is just a lock. So
Okay.
you don't have to. This is the back door. So you don't have to lock the door. Just like we used to do.
Okay. So any other passions while we're on it? Now, what I'm trying to get you to see is that if you're passionate about something, you will do it well, and you'll do it without somebody forcing. And if I've got to try and force you to get through matric, I can promise you, you're not going to get through matric well. You may just scrape through. But if you make it, you own it, it's your passion, I want to do well, you will do well. You cannot, I as a teacher do not have the power, apart from to try and explain things as best as possible. I haven't got the power to make you passionate about it and do a good job of it. Does that make sense? But I have found that the most boring things you can get passionate about. Now let's hope that physics doesn't fall into that category, that you are somewhat happy with it. And I told you yesterday I did a BSc. I loved science, but I was a very bad student, a very naughty student, because I used to just study the night before. I still had to get my C's and D's because you had to get a 50% to pass at this. So somehow we cheated the system, and then I did a BA later on when I was 35. I hated everything in the course. It was a 3-year course, Bachelor of Education degree. Nothing they said made sense to me. It was all rubbish. It was theoretical. I want to know, how do I teach a student? Give me a teaching method. Nothing like it. So it was a total waste of time, but I got all the A's and B's because my passion was to cheat the system and do well. So if they gave me a whole lot of gobbledygook, my passion was to go a month before the time and learn all this gobbledygook, spit it out again. And it wasn't uninteresting, but it was boring. And there we go. Okay, just let's have a look through this sheet that it's a workbook. Have you all put your names on it so you don't lose it? Now we can't have you losing these sheets, so it took us a bit of trouble to get it. Here's your BFF. We're doing Doppler. Do you see the Doppler equation here at the second bottom of the thing? What does it say is on top? V L over Vs. V listener over V source. So that is one equation you're going to use, and then just have a look above you. Above that it says V equals frequency times wavelength. V equals frequency times wavelength. What does that mean, anybody? Speed.
I think the distance
Distance is the what? The F or the L? Okay, so that's one of the formulas. Does anyone think they can explain V equals F upon L? It's not your fault because no one has explained waves at all to you. So the only thing you know is what we learned yesterday, as far as I know. So anyone know what V equals FL stands for? Velocity equals frequency times wavelength. I never really explained what is frequency. Anyone know what frequency is? Anneli, you do music. What is frequency when it comes to music? You sure? Okay. Thank you. Frequency is the pitch. And anyone from yesterday know how you get a high pitch? What is a high pitch? Lots of vibration. Does that make sense? So let's everybody, and you know why we act it out? Because it helps us to remember it. Let's get something to vibrate at a high vibration. Shall we do it? Okay, let's all do it. High vibration is as fast as you can go. That's a high vibration. Okay, and let's sing. Okay, great, you're doing well. Now let's get a low. Okay, now that's a good question. We are talking about something that's just got a single pitch. Like eeeew as it goes past you. Can we all do that, everybody? Let's go E as it comes towards you. Eeeew. Just do it again. Eeeew. And your homework is to go and listen to cars today as they come past you and see if it goes eeeew. Is Sir talking nonsense or not? Okay, now the actual note of the siren, which is one pitch, is not E and it's not oo, not U, it's in the middle. So let's do a vibration in the middle. What should we, it's E, O, U, oo, E, U. Let's do oo. So that's in the middle. Now that's the actual vibration. Can anyone think why you're hearing the actual vibration, the actual sound when the car is next to you? Wonderful. When it's just next to you and close to you, why are we hearing the actual sound, not the high or the low sound of it? Can you think of the logic for it?
So like parallel to each other, so you're getting the time.
Good guess. But I like what you're saying as well. It's parallel to you. Now, you're on the right clue, so just explain it.
Parallel to you, so it's like direct, opposite each other, so you're getting the direct sound.
Exactly. So if something's moving like this parallel to you, just do this parallel to you. Is this finger coming closer to you when it's doing this? Because it's parallel to you. Does that make sense? That's what she's trying to explain. But when it's coming towards you, is it closing the gap? Yes. But when it's next to you, it's doing nothing. It's staying 10 meters from you, right? It's not coming, or just slightly. So that's when you hear the oo sound. And then sing the lowest note you can make when it's going away from you. Ooh, ooh. Everyone? Ooh. And then do the vibration for that low note. Ooh. And that's what your eardrum is hearing ooh. And your eardrum is vibrating slowly as it goes away from you. Make sense, everybody? I'm going to ask any of you who remembered anything else from yesterday to just tell us what you remembered. Anything. I'm going to have to pay you today because you're teaching, and I'm going to have to give my wages to you.
When moving towards the sound source,
Yeah.
the frequency is higher. So
When moving towards the sound source, the frequency is higher. Now explain that to us, Vakila.
pitch is high, so
We hear the E. Now, why is that? Do you remember we explained it with a diagram? Now, can you remember why that is? Why does it make an E when it's moving towards you? Would you be able to, with a diagram, explain it? Anybody? Okay, Mikhail?
The time for to make the next wave is short, so that's why it makes an E sound. And when it makes a U sound, the waves are further apart, so therefore the sound it sounds lower.
Okay, just listen to what Mikhail's saying. He's saying it makes an E sound because, just explain it again loud.
Because the wave when it's high and the pitch is high, then the waves are closer to each other.
They're closer together. And why are they closer together?
Because the pitch is high.
Well, that's a circular argument. But it's because you're moving towards the wave and that's closing the distance. Or the source of the sound is moving towards you, so it's bringing the waves closer to the next wave. Does that make sense? Do you remember that? Make sense, everybody? Okay. And then just hands up, how many of you actually took the trouble to do the two little problems I gave you yesterday? Okay, so about 5 people. Okay, it's caught on camera who did it. Okay, so please, we need to do all homework.
So also I don't know if I said it talked about what you say the frequency of the listener. What is the frequency of
Okay, just let's explore that, Nelly. Is the frequency of the listener equal to the frequency of the source? When is the frequency of the listener equal to the frequency of the source? It's not always, but when? Fakila? When they're both standing still. In other words, when there is no Doppler effect. If you don't mind, guys, it does get picked up on the video if you're chatting. There's another time There's another time when, remember from this equation, frequency of listener equals something, frequency of the source. Who can tell me what must be inside that bracket? Okay, go to your BFF and just have a look what must be in there. I'm just going to turn this around. Okay, from now we know where to find this equation. Guys, please. I'm going to get you busy in a moment doing some work, but just let's keep this quite quick. Okay, so they don't put a bracket, they just have it V plus, minus, and then they got VL and VS. Okay, I put a bracket around it, they don't, I notice. What other time did we say that this equals that, at which point is it equal? Velocity of the source, and, frequency of the source and frequency of the listener. E-oo is the actual sound. Ew. Ew. So at this point, that equals that. Now the question is, all the stuff in the middle, what did I say that it is? Forget what it actually is. What's the ratio? What does it mean, all those things in brackets? It's a number, it's a fraction, right? Do you remember my saying that? Yep. And remember I said to you, if this is greater than 1, then it is coming towards you or away from you. If this is greater than 1 times frequency of the source, will this be higher or less? Come on, mathematicians, think about it. If I make this, say, 1.3 times, let's make this 1,000. 1.3 times 1,000 is going to be 1,300, right? So the moment this is greater than 1, it's coming towards you. When it's equal to 1, all this junk in the brackets, then it is stationary or coming next to you, parallel to you. And when it's less than 1,
It's getting away from you.
less than 1,
So what?
it's going away towards, and this is next to or parallel. Easy enough? And that is what we need to, this is the equation that you're going to use, plus maybe this equation B equals frequency times wavelength. Now when I went home yesterday, I thought I didn't really very well teach you frequency. Just let's see if we can demonstrate frequency. Anything that vibrates produces a sound. Okay, I can't produce a very loud sound, so, but watch this as I make it, listen to the sound. Did you hear what happened to the frequency? Thanks a lot. Just listen again. Did it go higher or lower? It goes higher. As this gets shorter, it vibrates faster. As this gets shorter, it vibrates faster. This is a very poor example of a musical instrument. Then you could also demonstrate, but you can't see it. Slow vibration, high vibration. You've demonstrated this one is doing very high, this one is doing slow. In the hospital, what? Are you thinking about the heart? Okay, well, there's an example. Say you've got your heart, and it's doing that with a frequency of 60 hertz. Then that means your heartbeat is 60. Well, let's just go with this. It means that your heart is going at 60 beats per minute. That would be the frequency. So this symbol here is the frequency or the number of beats per second. That's the frequency. What is the wavelength? The wavelength, we said, is, imagine you've got like a dripping tap. And every time the drip falls in, it creates a ripple. That is the wavelength. Does that make sense? So the more often it drips, the higher the frequency. What's going to happen if my tap is now dripping faster?
The wavelength will be closer.
Then your wavelength will be closer. So your wavelength will be smaller. Does that make sense? And then we use, there's one last formula here, which is T equals 1 upon F. Now, did we mention what T is? T, remember we said, is the period. So if, let's just say, here's your ear. If this is your ear, the frequency is the number of waves that passes your ear per second. That's the frequency. The period is the length of time it takes for one wave and then the next. The time between waves is the period. So look at this formula here. Period and frequency. The higher the frequency, the bigger or smaller the period?
The smaller.
The smaller. So it's an inverse relationship. Do you see that? Are you familiar with inverse relationships? And you can see it. The time between waves is going to be shorter if your frequency is higher. So there are your three formulae associated with Doppler. Everyone happy? Then let's just turn over. There you see a few more formulae. Okay, then you'll see here how your child in matric can do better. Read through it. Won't you read through it? Then here are some definitions in caps. Let's see if we can find any to do with Doppler. Can you see we've got some momentum, we've got some Newton definitions, we've got some waves. Okay, here it says waves. State the Doppler effect as the change in frequency or pitch of the sound detected by a listener because the sound source and listener have different velocities. Does that make sense? So there's like a definition. I don't particularly like that. So I'm on page 1, 2, 3, 4. Then here we've got some more definitions. Just page through this with me. We've got some physics, we've got Newton's laws, learn them. Now you see guys, you have to know these. Please guys. And again, I see the reason why spreading you out is actually not a bad idea, because it's the people sitting close together and facing backwards who are always the ones chatting. Okay, so then there's definitions. If you're a passionate student, you've got to go home and learn those definitions. These are, actually they ask these definitions. Let's just see if we can find any on Doppler effects. They just give another definition. Let's just try and read this one. It says at page something 2 or 3. Doppler effect. The Doppler effect with sound is a change in frequency or pitch of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay, they would accept that definition. I can give you a better one. And then there's some chemistry definitions on the next page. Just page through it. And then all of those we need to learn. And then there's a few more chemistry definitions. And then we come to vertical projectile motion. Are you there? Some pages I may have stapled just a little bit different order. Although this is a memo, read through it and just see if you would have got those answers. Then there's another thing called lesson 1, which is it's asking you a few things, and then it starts with momentum, and it's got a problem there with a log on the next page. Then we come to the photoelectric effect, which we're going to do soon. We're going to get to it. I'm just going through what we got, then a little, unfortunately, upside down, the rest of the photoelectric effect. Coulomb's law, I believe you've done.
Yes.
So why not go and see if you can do it? Work through the Coulomb's law worksheet. Then we come to the exemplar of 2014. Question 4, 2 boys of maths. So, hello. So we've got a momentum problem, question 4. Questions? I will give you a statement in a moment. Okay, so we're going to work through the exemplar, question 4. Now, what I want you to do, you see that momentum problem. See if you can do it. So, are you with me? See if you can do it. You've done momentum, see if you can do it. You can't do question 5. Let's just have a look at question 6. Here's a Doppler question. From the exemplar. Let's just read it. It says, the siren of a stationary police car emits sound waves of wavelength 0.55 meters. Now, guys, you must get to a point where when you see that, they're giving you the wavelength, they're going to give you the velocity. Just let's read if they give us the velocity somewhere.
Is that 45 meters?
They say assume the speed of sound is 345. Okay. Now, can you work out the frequency from that? Can you? From that formula. So you know the wavelength. Yes, it's in meters, correct unit. You know the velocity of sound, it is 345, so you're going to work out the frequency. That's the actual frequency, meaning which one of these? That's the frequency of the listener or the frequency of the source? Frequency of the source. So Misha is on the ball here. Are you with us? You with us so far? So even before I have read further, I know I'm going to have to use that to plug it into this equation. All Doppler questions will use this equation, but they're going to make you go through a step to get to that. So in this case, they've made a little step. Okay, let's read on. Will the wavelength of the sound waves observed by the listener be greater than, smaller than, or equal to 5.5? Well, let's see. Is the car moving towards? It says when the siren's on the police car now approaches. So what did we say when something's coming closer? And then are the wavelengths shorter? The wavelengths are shorter, but the frequency is higher because it applies to here. If the wavelength is shorter somewhere, the frequency will be higher. So, will you be able to answer that? Will the wavelengths of the sound, when observed by the listener, be greater than or smaller than or equal to 0.55? You can work out the answer. Will you be able to work out the answer, Jamie?
Yes, sir.
So, if it's coming towards you, it's shortening the wavelength and increasing the frequency. So, there's your answer. So, you're going to fill that in. Name the phenomenon. What is this phenomenon called? Doppler effect. 5.3. Calculate the frequency of the sound waves observed by the listener if the car approaches him at a speed of 120 kilometers per hour. You see, they're making you jump through a few hoops. You've got to change it to meters per second. And where will this go in this equation? Where will it go in this equation? Calculate the frequency of the sound waves observed by the listener if the car approaches him at a speed of 120 kilometers. Which of those is the speed that the car is approaching him? The velocity of the source. Well done. So change it to meters per second. You know how to change kilometers. You're going to multiply by 1,000. You know you're going to change hours to minutes. You're going to, are there more? You're going to multiply by 60 and 60 again to get to seconds. Hours, you multiply by 60 to get to minutes. Multiply minutes by 60 to get to seconds. And then 6.4, how will the answer in question 6.3 change if the police car now moves away? You can work that out. Okay, do that question now. So that is the exemplar. Just do it on this page. So you see, you can do everything.